Hello, my name is Christina Nielsen, and this is my Physics 2211 Lab 4 over oscillations. To start, the purpose of this lab was to model the 2D motion of a swinging spring mass system that oscillates back and forth. The result of this lab was that we found that there was a little derivation in our data and the tracker data. However, our computational model was able to successfully predict the motion observed in the experiment as a whole. Now for some fundamental physical principles. First we have Newton's second law. Next we have Hooke's law that works with springs, as you can see on the right in that image, and the energy principle that says that delta E is equal to W plus Q. Here there's nothing in our surroundings, so delta E should be equal to 0. Therefore, delta K plus delta U spring plus delta U grav should also equal 0. And we will get more into that later. For glow script part 1, we first laid out our initial conditions, the initial mass of the ball, the position vector, velocity vector, delta T, spring constant, and relaxed length of spring. And all of these values were derived from our tracker data. The system in this lab is the spring ball system, and the surroundings is just the earth and air. And here on the right is a picture from tracker directly. For our calculation loop, we first had to calculate the gravitational force and the spring force. Then we found the net force. From there, we were able to update velocity and position with the momentum principle. Then we updated spring length and direction vector L hat. And then finally, we calculated and plotted the energies U grav, K, U spring, and E. For our results, on the left, you can see the two graphs for the X position and Y position comparing our model's data and the experimental data. As we can see, the computational model and the experimental data are very similar in the beginning, but begin to deviate as time goes on. The change in X position begins to slow down, and the max Y position for each oscillation decreases. Now, for some possible sources of error that would explain this. There could be work done by the surroundings that is not accounted for in our data. Or there could have been some inaccuracies when manually plotting the position for the center of the mass of the ball in tracker originally. Now for some questions. Is the energy principle satisfied? On the left, you can see that tracker was able to plot our energy data in different colors with delta K, delta U grav, delta U spring, and delta E. We can see that yes, the energy principle is satisfied because since no external forces are acting on the system here, the work done on the system should be 0, and therefore the change in energy, or delta E, should also be 0. We can see in this graph that delta E, the yellow line, is constant at 0, meaning the energy principle is satisfied here. Now, to compare oscillation periods. I was able to calculate average oscillation periods by looking at the time it took for the spring ball system to get through 3 periods, and then took the average time for each period. The average oscillation period over 3 periods in the X direction is about 1.646 seconds. And the average oscillation period over 3 periods in the Y direction is about 1.520 seconds. Now, having different oscillation periods in different directions would ultimately affect the spring constant from the spring energy equation and the graphs, showing some deviation and throwing off our data. Thank you.